Hey guys, so this is section 8.6 using the Clausius Clapeyron equation to calculate vapor pressure as a function of temperature. So we start with the Clausius equation, which we derived in the last section, I believe, right up here. Rearrange it a little bit, take the dt on the other side, integrate, and by the way, when we're integrating along the, we're starting out with the solid-liquid coexistence curve. So this is right along that coexistence curve. Integrate the dP from some initial to some final pressure, the right-hand term, the dt term, from some initial to some final temperature. What we do here is we know that along that coexistence curve, delta S is equal to delta H over T. So we replace delta S inside the integral with delta H over T. That gives us something we can integrate easily. We're going to assume, it's a pretty good assumption along that coexistence curve, that delta H and delta V are, they don't change much within this temperature range, Ti to T final. So this is what we have. When we integrate, we have P final minus P initial, which is just delta P. Again, we're assuming delta H and delta V are don't change along the, within that temperature range. Get natural log of the final temperature over the initial temperature. And we can write the final temperature as the initial temperature plus some increment, delta T, where delta T is T final minus T initial. And you'll see why that's nice in a moment. Rewriting this a little bit, P final minus P initial, delta H of fusion over delta V of fusion. It's fusion because it's a solid-liquid coexistence curve. Natural log of 1 plus delta T over Ti. All I did here was, Ti over Ti is just 1, and then delta T over Ti is this term right here. Then we get to use a nice property of natural logs, and that is that natural log of 1 plus x is very close to being just x if x is a lot less than 1. The reason for this is because you can write a natural log as a series expansion called a Clapeyron series, where natural log of 1 plus x is equal to x minus x squared over 2 plus x cubed over 3 minus plus, etc., etc. And if x is a lot less than 1, then the second order terms and above are very small, because you're squaring it, cubing it, and then dividing it by some integer. So it's a good approximation, and we'll take advantage of it. So that gives us that the P final minus P initial is equal to delta H of fusion over delta V of fusion times just delta T over the initial temperature. And again, remember, we're assuming, and it's, we can do it this way, that delta T is a lot less than 1. So one thing that shows us is that the vapor pressure of a solid, the delta P, varies linearly with the difference in temperature when the difference in temperature is small, a lot less than 1. We can do the same sort of analysis for the liquid-gas coexistence curve, starting with the Clausius equation, rearrange it, and do everything we just did, and we end up with this term right here. So let's look at this. Delta H vaporization over T, delta V vaporization. We haven't integrated yet, by the way. So all we did was said with delta S is delta H over T. Now what we can do here, because remember we're going along this coexistence curve from a liquid to a gas, delta V is the volume of the gas minus the volume of the liquid, but the volume of the liquid is negligible compared to the volume of the gas because the gas occupies so much more volume than the liquid does. So we can just replace delta V of vaporization with the molar volume of the gas right down here. And assuming ideal gas law behavior, if it's not, then the algebra just gets more messy, but we could do it. The molar volume of the gas is equal to RT over P, so PV equals nRT, N is 1 because it's a molar volume. So we can replace the molar volume of the gas with RT over P. So RT, there's already T there, so it makes it T squared. The P goes on top. And we get this term right here, okay? And that's delta H over T. Molar volume of gas is this. So plugging that term in here, setting it equal to dP over dt, and bringing the dt over to the other side. Now we have something we can integrate. And again, along the coexistence curve. So we're going to integrate dp over p from pi to p final. We're assuming, again, the delta H of vaporization does not change appreciably over this temperature interval, dt over t squared, which gives us natural log of the p final minus p initial is equal to negative. That's because when integrating t to the minus 2, we get the negative in front. Delta H vaporization over R times 1 over t final minus t initial. Or if we take e to both sides, we get p final over p initial equals e to the negative delta H vaporization over R, 1 over t final minus 1 over t initial. Real quick word on the sign, guys. A lot of times I bring this negative sign inside the parentheses, so it's positive out front, and these terms just swap places, but that's identical. So for sublimation, we can say same analysis. The only difference is now it's delta H of sublimation rather than vaporization. We get a Clausius Clapeyron equation for sublimation, going from a solid to a gas. And like with vaporization, we assume that delta H of sublimation is independent of temperature. All right, so let's do an example. We're given the normal boiling point of carbon tetrachloride. That remember, normal boiling point means the boiling point at 1 atmosphere of pressure above it, or 101,325 pascals. Its vapor pressure is this number, 15,280 pascals at 2.15. Delta H of fusion, vapor pressure of solid carbon tetrachloride at 270 is 270 pascals at 230 Kelvin. So we're going to calculate the heat of vaporization of carbon tetrachloride, change in entropy of vaporization of carbon tetrachloride, and the triple point temperature and pressure for carbon tetrachloride. So first thing we're going to do is get heat of vaporization using the Clausius Clapeyron equation. So there it is, and I've done what I just talked about a minute ago, guys. I just brought that negative sign inside the parentheses, and these terms switch places. Rearranging the Clausius Clapeyron equation to solve for heat of vaporization, you get this. So for the vaporization, the final pressure is, so what we're doing, okay, so with the Clausius Clapeyron equation, we need two pressures, and vapor pressures and two temperatures. So the vapor pressures we're going to use are the vapor pressure at 298.15 and the vapor pressure at its normal boiling point, which is 101,325 pascals, 1 atmosphere. And the temperatures are the associated temperatures. Plugging that in, and please check my math, I end up getting 31.76 kilojoules per mole. So that's our heat of vaporization. Once we have heat of vaporization, the change in entropy of vaporization is easy. We just divide the heat of vaporization by the boiling point, and I get 90.81 or so joules per Kelvin mole. Now, okay, the triple point pressure and temperature. So we're going to take advantage of the fact that at that triple point, the vapor pressure of the solid is equal to the vapor pressure of the liquid, and that we're going to call the triple point pressure. So writing the Clausius Clapeyron equation for the liquid right here, and then the Clausius Clapeyron equation for sublimation, solid to gas, right here, and we subtract this equation from this equation. On the left-hand side, what I've done is, because natural log of A over B is natural log of A minus natural log of B, I've written this term and this term as natural log of the top pressure minus the bottom pressure. But, okay, because the vapor pressure of the solid and the liquid are the same at the triple point, which is just the triple point pressure, this term here, which came from here, and this term here, which came from here, cancel. And on the left-hand side, we just get the natural log of the sublimation, the pressure for sublimation over the natural log of the vapor pressure for vaporization. And when we subtract the right-hand sides of the equation, it's just this term minus this term. That's what we have over here. All right, so that's where we're at this point. And that's this equation up top. Now it's pretty much just algebra. I multiply through by R, bring it over here. I distribute the delta H's inside the parentheses, collect like terms. So delta H of vaporization over the vaporization temperature, that's from here and here, minus a delta H of sublimation over the temperature of sublimation right here. Remember, we already pulled the R over. And then what I did was everything that had the triple point temperature, which is delta H of vaporization here and delta H of sublimation here, I pulled the 1 over the triple point temperature out, and I got this term in parentheses. Divided, so I added this, subtracted this, that's where these terms came from, then divided through by the parentheses, and we get this equation right here. See, we're isolating the triple point temperature. And then this is 1 over the triple point temperature, so now I cross multiply or invert both sides, and I get this equation right here. Now we have something we can plug into because we know all this stuff. We know R, we know the pressure of sublimation, 270 pascals, we gave that. The pressure of vaporization at 298.15. Note that we could have used in this equation the boiling point. That temperature would be 349.79 Kelvin here and 101.325 pascals here, and we get the same result. Just the same number. Anyway, so check my math. I end up getting 281 Kelvin or so for the triple point pressure. We're almost there. Now to get the triple point pressure, all we do is use that good old Clausius Clapeyron equation where our 2 points are going to be the triple point and the boiling point. So we use, natural log of P final over P initial equals delta H of vaporization over R, 1 over T initial minus 1 over T final. Initial is a boiling point, final is a triple point. Plugging in the temperatures, delta H of vaporization, which we got in the first part of this problem. And I end up getting that the triple point pressure is about 7 times 10 to the third pascals. So, the boiling point pressure is just, again, 1 atmosphere, 101, 325 pascals. And there we have it.